Hello everyone, welcome back to NoSketch. So let's solve another problem from graph and trees from Uber Frequent 52 premium card. So let's see what the question is and how we can approach to that problem. So today we are going to solve serialize and deserialize N-ary tree. So first let's read the problem statement and then we'll understand the problem. Serialization is a process of converting a data structure or object into sequence of bits so that it can be stored in a file or memory buffer or transmitted across a network connection linked to be reconstructed later in the same or another computer environment. So design an algorithm to serialize and deserialize or serialize an N-ary tree. An N-ary tree is a rooted tree in which each node has no more than n children. There is no restriction on how your serialization and deserialization algorithm should work. You just need to ensure that N-ary tree can be serialized to a string and this string can be deserialized to the original tree structure. For example, you may serialize the following 3-array tree. So 3-array means your every node in the tree can have at most 3 children. That means no more than 3 children, right? If we are talking about 4-array tree, so if you will see, every node can have at most 4 children, no more than 4 children, right? So let's see the constraints. The number of nodes in the tree should be in the range of this. Node value should be in the range of this. The height of N-ary tree is less than or equal to 1000. Do not use class member global static variables to store states. Your encode and decode algorithm should be stateless. Okay. So this point we'll see when we'll code it, right? First let's understand the problem statement and let's see how we can serialize and deserialize our N-ary tree, right? So let's say this is our tree, right? So serialization means given a tree, convert that tree into a string. Serialization means given a tree, convert that tree into a string. This tree can be 2-array, this tree can be 3-array, this tree can be 4-array, right? So this tree can be N-ary tree and we have to convert this N-ary tree into this string. Right. Now what does deserialization means? Deserialization means you have that serialized string. You have that serialized string, right? And you will have to convert that back to a tree, back to a N-ary tree, right? So this is the meaning of serialization and deserialization, right? So if some people might think that we can, we can directly traverse the tree. We can directly traverse the tree by using any method like pre-order, post-order, in-order, and you can create a string. So let's see when we'll do this, what will happen. So when we traverse it in pre-order, okay, so since this is an N-ary tree, the node structure which will look like something this. Node, right, will have one value, let's say in 12. This is 1, 2, 3, 4, 5 and we have a list of children. List of children. So this will be the structure of node for an N-ary tree, right? So let's see how we can traverse this tree. So let's say we are starting from 1. We are starting from 1, let's print 1. Then our pointer will move to the 2, right? If we are printing pre-order, right? So 2. Then there is no other child for 2. So we'll come to the next child of 1. So it will print 3. Then we'll go to the left of 3. So it will print 6. Then we'll go to 7, right? Then 7, after 7 we'll explore the children of 7, 11 and then 12, right? So 7, 11 and 12. Then when we are finished exploring all the children of 12, we'll go back to the next child of 1, so which will be 4, right? Again we'll come to 8, then 13, then 5, right? So in this way we are traversing it. 4, 8, 13, 5. Then we'll explore the child of 5, so it is 9, then 14 and then 10. 9, 14 and 10. So now this is the DFS traversal, basic DFS traversal of this N-ary tree. But now let's say given this string and I am saying you will have to convert back to the same tree. So can you do this? Given this string, can you convert this string back to this N-ary tree? No, because you don't know what are the childs for 1, right? Somebody can think of 1, then 2, then 3 is a child of 2, then 6 is a child of 2, right? In the other case, any other people can think of 1, 2, 3, then 3, 6, right? 7, 11, 12. So there is no meaning to this statement. This is just a traversal, right? This is not informative to us. This is not telling which node is a child of which node or which node is a parent of which node, right? So we should know that which node is a child of which node and where for a particular node the processing has been stopped. So let's see what we can do, right? So let me create, we'll call the DFS and we'll see how we can do it. So let's say this is our DFS call stack, right? We'll again start with our very first node. Right? So now the first call will be made for DFS1, right? Now DFS1 we'll print 1. Now after printing 1, I'll explore all the children for 1. So first child is 2, right? First child is 2. So second call will be DFS2, which will be pushed to our stack, and 2 will be added to our string. Right, now let's see what will happen. So now there is no left or right child for 2. That means this node has, the processing for this node has been completed. The processing for this node has been completed. So that means this will be popped out from this stack. This will be popped out from this stack, right? And we'll append hash. When the processing for any node has been completed, we'll append hash. And that way we would know that there is no child. When we'll start traversing the string, right? So we'll know there is no child for 2. There is no child for 2, right? Okay, so after finishing this, we'll come to the next child of 1, because at the top 1 is present right now. At the top 1 is present right now, right? So now after completion of DFS2, we'll push the call for DFS3 will be made, right? Now for DFS3, 3 will be appended to our result, and we'll explore the children for 3. So there is 6. So now DFS6 will be pushed. I mean DFS6, the call for DFS6 will be made, and there will be 6. Right, now if you will see there is no child for 6, right? So that means the processing for 6 has also been finished. Processing for 6 has also been finished, and this will be popped out from the stack, right? And when the processing is finished, at the end we'll push hash, right? Okay, then we'll come to this 3 back, because at the top there is 3 present. At the top there is 3 present. We'll see, is there any other child for 3? Yes, there is one more child for 3, which is 7. So now the call for 7 will be made, and the call for 7 will be made. So let's push DFS7 to our stack. Perfect, right? Let's come to this. 7 will be appended to our string, right? And then there is other child for 7, which is 11. So let's call DFS11. 11 will be appended to stack. Then we'll call 11 for 12. So DFS12, and 12 will be appended to stack. Now again we'll see, is there any other child for 12? No, there is no other child for 12. That means the processing for 12 has been finished. The processing for 12 has been finished, right? And we'll append hash to our resultant string. Perfect. Okay, the call for 12 was made from 11, so we'll go back to 11. So is there any other child for 11 to explore? No. That means for 11 processing has been completed. So we'll again append hash, right? And it will be popped, because the processing has been completed, so it will be popped. So let's come back to 7. Is there any other child for 7 to be explored? No, there is no other child. For 7 also the processing has been completed. So we'll again, okay, so when we are going back, right, so there will be a pop from this stack, right? So now 7 will be popped. Let's go back to 3. So is there any other child for 3 to be explored? No, there is no other child for 3 to be explored. So this processing has also been completed. We'll append hash and we'll pop it from the stack, right? So now the stack current state is this. At the top there is 1, right? So now the call will go back to 1. Is there any other child for 1 to be explored? Yes, which is 4. So we'll push DFS 4, right? And then append 4 to our result, right? Then is there any other child for 4 to be explored? Yes. Then 8. So DFS 8, right? Push 8 to a string. For 8, we'll explore the child of 8, DFS 13, right? And 13 will be pushed. Now for 13, there is nothing to explore, right? That means the processing for 13 has been completed. The processing for 13 has been completed. It will be popped and hash will be appended, right? It will go back. Is there any other child for 8 to be explored? No. That means it is also finished. We'll append hash. When it will return, we'll append hash and it will be popped from the stack, right? Is there any other child for 4 to be explored? No, there is no other child for 4 to be explored. So again, it will be popped, hash will be appended and it will again go back, right? Is there any other child for 1 to be explored? Yes, there is 5. So let's come to 5. Let's come to 5, append 5 to the call for 5 to be made, right? And 5 will be appended. Then we'll come to 9. DFS 9 will be called, right? DFS 9 will be called and 9 will be appended. Then we'll come to this 14. DFS 14 will be called and 14 will be appended. Now, is there any other child for 14 to be explored? No. That means 14 is also completed. So we'll pop 14, we'll append hash, right? Is there any other child for 9 to be explored? No. That means 9 is also finished. We'll pop 9 and we'll append hash, right? Now the current state for our stack is this, right? So at the top there is 5. So let's go to 5. So is there any other child for 5 to be explored? Yes, there is 10. So DFS 10 will be made, right? 10 will be appended. Now is there any other child for 10? No. So 10 will be deleted and hash will be appended, right? Again the call will go back, so 5. So is there any other child for 5 to be explored? No. So we'll append hash. Now we'll go back to 1. So is there any, okay, 5 will be popped. So now the current state for our stack is this, right? So is there any other child for 1 to be explored? No. So that means processing for 1 is also completed and it will be popped from the stack. So this will be our serialized string. This will be our serialized string, right? So let's quickly code the serialization of the string and then we'll understand deserialization and we'll code for deserialization. Okay, so for serialization we'll be needing one string builder because we cannot, we cannot modify our string. So we are taking string builder, right? And we are making one DFS function. Let's say I am saying serialize util to it, serialize util, right? I am passing root and also I am passing string builder, right? And finally I am returning sb.toString because we want to return string, so we'll have to convert this string builder to string again, right? So let's create function. Okay, the serialize util, right? It is taking node, root node, and it is taking string builder. So first of all we'll check whether if root is equals to null. If root is equals to null, we can simply return. Otherwise what we'll do, we'll append the result to a string. So sb.append, what we want to append? We want to append sb, this is string builder, right? sb root.value plus 0 and we want to append it to our string, right? After appending, what we are doing, we are exploring each and every children for this root, right? Node child for this root, right? We are accessing the children's list for this root, right? And we will get this child, right? So for every child, what we are doing, we are again calling the util function. Let's call the util function, which is basically for child and for sb, right? And at the end, when all the nodes have been processed, let's say for this particular node, there is no other thing to be processed, right? So what we did before returning back, we appended hash, right? And then we return back. So let's do it. Let's append sb.append hash to our result. So this is how you can code it. Basically for serialization util, what we are doing, for every node, we are appending its value to a string builder. Then we are exploring each and every child of that root. And then at the end, when all the processing has been finished, I am appending hash to it. That yes, for this particular node, all the processing has been finished, right? Okay, so now let's understand the deserialization. So now we have the serialized string. We have this serialized string. Okay, before going to deserialization, let's discuss the time and space complexity. So time complexity will be, if you'll closely look, what we are doing, we are traversing each and every node present in the tree. We are traversing each and every node present in the tree. So the time complexity will be O of n, right? The time complexity will be O of n. And what will be the space complexity? Space complexity will be the call made in the call appended to a stack, right? So it will be O of n, which is a stack space, right? And this is for traversal. So this will be the time complexity for serialization process, right? So now let's understand deserialization and then we'll discuss the time complexity. Okay, so this is a string given. Let me write index for each of the value. Okay, so we'll start from 1. When we are at 1, we'll create a node 1, and for 1 we'll be having this empty list, right? List of children. So now we created a node. We'll move to the next one. After creating a node, we'll move to the next one and we'll do the same thing. So first step will be create a node, increment the pointer. This is our first step. So again we are at this 2. Right? So what we'll do, we'll create a node, there will be empty list and we'll increment the pointer. But before incrementing the pointer, we'll add this 2 to the list of children. Add to the list of children, right? Okay, then second, now we have hash. So when we have hash, we know the processing for 2 has been completed. There is no other child for 2 for being processed, right? So that means in this case, the processing for 2 has been finished, right? So we'll again come back to this one. And we'll explore other indices. Right? So what we did, when there is a hash, we'll come back to 1 and we'll explore other indices. So let me tell you what will happen, right? So first call that was being made was for DFS1, and when this call was being made, we created this node, right, and we moved our pointer to next one. Second call was for DFS2. So for DFS2, we created this node and we added it to our child list, right? Now third call for DFS hash. So when DFS hash was being called, right? Okay, rather than calling the function, let's create one while loop, that until we encountered this hash, right? So when we encounter this hash, we'll pop it. That means the processing has been completed, and we'll simply increment the pointer, right? So let me write the simple steps. So we call the function for our 0 index, right? We call the index for our 0 index, and then what we did, we created a node for the value at 0, right? After that, what we are saying, until the value spu.char at let's say index is not equals to hash, right? We'll call the same function. But when it is equals to hash, we know the processing has been completed, so we'll come back and we'll return node. So this is what we are trying to do, right? So after 2, when there is hash, the processing has been completed. So at the top there is 1. So now we'll come to this 3 and we'll again create this node. So we'll create 3 as a node and an empty list with it, right? Now come back, let's go back to next pointer, which is 6, right? So now at 6, we are currently at 3, right? So we will create a node 6 with an empty list. We'll create this 6 to the children list of this 3, right? We'll add this 6 to the children list of 3 and we'll increment our pointer, right? Hash. Now this is hash, so that means we know the processing for 6 has been completed. So we'll again come back to 3, and the pointer will get incremented, so it will come to 7. Now since we are currently at 3, so we'll again create one node, which is 7, right, with an empty list, and we'll add this 7 to our list. We'll add this 7 to our child list. Now let's come to this 11. When we'll come to this 11, at the top the call will be for 7, right? So we'll create the 11 with an empty list and we'll add this 11 to 7. Let's come to 12. Now at the top 11 is there, right? 11 is there, so we'll create 12 with an empty list and we'll add it to our 11th list. Now let's come to this hash. So when we'll come to this hash, we know the processing for this 12 has been finished, right? Let's come to next hash. We know the processing for this 11 has been finished, right? Let's come to next hash. For next hash, we know the processing has been finished for this 7. Let's come to next hash. The processing for this 3 has been finished, right? And we'll again come to this 1. So from this one, we know this 4 came. We are currently at 4 and this 4 came. So we'll again create this node with an empty list, add it to the child list of 1, right? And we'll move ahead. So when we'll move ahead, we encountered 8. So currently at the top there is 4. So we'll create a node and add it to the list of 4. Then we'll come to this 13. At the top there is 8. We'll create a node 13. We'll add it to the list of this, right? Let's come to this hash. That means the processing for this 13 has been finished. Okay, so these lists are basically the children's I am adding, right? So for 7 the list contain 11, for 11 the list contain 12, right? If at this point this list will contain 2, 3 and 4. This 2 will be empty. For this 3 there will be 6 and 7, right? For 6 this is empty. For 7 we have 11. For 11 we have 12. For 12 we have empty. Again for 4 we have 8, right? In the list. For 18 we have 13, right? Okay, so after this the processing for 13 has been finished. At this point the processing for 8 has been finished. At this point the processing for 4 has been finished, and again we are at 1, right? So currently we will be at 5. So again we'll create a node 5, add it to the 1's child list, and then we'll move ahead. So when we'll move ahead, we will come across 9. So let's create a node 9, add it to the child list of 5, right? Let's move to 14, create a node 14, add it to the list of 9, right? Let's move ahead. So hash, that means 14 has been finished, right? Let's move ahead. There is one more hash, that means 9 has been finished, right? there is one more ahead. Okay, so next one is 10. So currently we are at 5, so that means this will be the child of 5. So let's create 10, right? Let's move ahead. So we have hash. Hash means this has been finished, right? For next one we have hash, this has been finished, and okay, there will be one more hash to it, right? And there will be one more hash. So when we'll come to this hash, we'll know the processing for 1 is also finished. And this is the tree we got from, serialized string. So first let's try to code it, right? And then we'll discuss the time complexity. So for serialization, first of all, let's check whether this is empty. If this is empty, if this is true, we can directly return null, right? Otherwise, we'll call Deserialize util function, which will take data and an index. Okay, so now if you'll see, do not use class member, global, static variables to store states, right? Your encode and decode algorithm should be stateless. That means we cannot use variables for maintaining the state. So what other than this, what options we have? We cannot use member variables, we cannot use global variable, we cannot use static variable. So now we are left with class, right? So we can maintain a object, let's say int value, right? Let's create a constructor. This will set the value. Let's say we are passing int value, this dot value is equals to value, right? Let's call get function, so it will get value, this dot value, right? Let's make one increment function that will increment our variable. So void increment this dot value plus is equals to 1, right? Now let's pass this this object new int value. This will hold the value 0 because we are starting from 0 index, right? Now let's write the function for deserialize util. So private, it will return node string st is equals to, let's say we are calling it data only. We have one variable int value, or let's say we are calling it as index, right? Now first of all, if this index dot get value is equals to data dot length length, so we can return null. Otherwise we'll create a node, new node of what? The value at that particular index, right? New node data dot char at index dot get value, right? We'll convert it into an integer, right? After this, what we'll do? We'll keep on exploring next. Okay, we'll increment the index. So index dot increment, and then we'll keep on exploring the next indices. So while data dot char at get value is not equals to hash, we'll keep on exploring, we'll keep on calling the same function, data dot data comma index, right? And then we'll keep on, whatever the value will be returned, we'll keep on adding it to our node dot children, right? Node dot children dot add. And when we are creating a node, we'll initialize this list of nodes, right? And after this, we'll again increment, because if it's not equals to hash, we'll be getting one hash. So in that case, we'll have to increment it. So let's increment it and let's try to run it. It cannot find symbol. I guess we forgot to. Perfect. So int value, and let's return the node from this point. I hope now it will work. Yes, and we got our result. Let's try to submit it, and it is accepted. Okay, so let's discuss the time complexity. So if you'll closely observe, for every node we are traversing this string throughout, yeah, right? We are traversing this string throughout. So for every index we are traversing, right? And we have this hash. How many hash will be there in this string? This is a unique character which is telling that the processing for this particular node has been finished. The processing for this particular node has been finished, right? The processing for this 12 has been finished, 11, 7 and then 3, right? So for every node, for every n node, we have n unique character, right? And we are traversing each of it, right? So the time complexity in the worst case will be O of n. And what will be the space complexity? O of n for our stack space, right? O of n for our stack space, and this is our result, right? This is the need for the question. So O of n for this state. So the time and space complexity for this problem will be O of n and O of n. So same for serialization and same for deserialization. So this is how you can deserialize and serialize your tree with the help of DFS approach. But we have one more approach which is using BFS. So in the next video we'll see how we can deserialize and serialize our tree with the help of BFS. So I hope you like this video, you learned something new from this video. In the next video we'll discuss the BFS approach. So yeah, that's it for this video. Till then, keep learning. We'll meet in the next video. Thank you.